So let me go to the first speaker today. The first speaker is Professor Kazuto Yamauchi. He's already with us now. He will deliver atomically ordered surface formation by catalyst-assisted chemical etching. He's from Department of Precision Engineering, Graduate School of Engineering in Osaka University. His research area and expertise actually uh, summarized in these five interesting topics. First is atomistic production technology, giant scale nanotechnology, application to semiconductor device processing, X-ray optics and optical system, and X-ray nanoscale biology. So without any further hesitation, we would like to welcome Yamauchi Sensei to deliver your lecture. Yamauchi Sensei, times is yours.
Thank you very much for the kind introduction of me. And can you hear me? It's okay? Good morning.
Yes,
Good morning. It's okay. So I'd like to use my PowerPoints. So can I use?
yes, you can share.
Okay. You see my.
We can see.
Oh, yeah. But uh, okay. You can see.
Yes, Sensei, we
Okay.
can see you.
Okay. I'm Kazuto Yamauchi from Osaka University. So the I'm howling. So please off your microphone.
Hmm.
Okay. Okay. So today's my talk is on the atomically controlled surfacing of functional materials by catalyst-assisted chemical etching, named CARE process. The title is a little modified from the original one, but it is changed to be more easy to be understood. It's okay? Nearly the same title. Okay, so I'd like to start my talk. Devices, maybe electronic devices and optical devices, nearly all of them uses the function of the material of the substrate, and they are prepared on the substrate. So maybe you can imagine device performance is significantly depending on the surface quality of the substrate. And so on the substrate, geometrically and crystallographically highly ordered surfaces are indispensable, strongly demanded. So today's topic from me is a chemical method to realize perfect surface of various functional materials. Okay, so I'd like to start. This is preparation technology of the substrate. Crystal is sliced, ground, and lapped, and finally we use chemical mechanical polishing method. This is called to be CMP, and CMP uses slurry with fine powder particles and chemicals. And this method can reduce the roughness of the substrate and is good for the geometrical sense. And also this method can reduce the damage induced in the lapping process. The lapping process is used for the flattening, but it uses diamond particles. So lapped surface has strong damage, mechanical damage due to the diamond particle scratching. So this kind of damage should be removed, and CMP can reduce the damage of the lapped surface. But there are some disadvantages. CMP still uses powder particles, so damage still remains. And due to the usage of the powder particles, cleaning is so difficult. So our challenge to overcome this kind of problem is to realize chemical finishing method without any powder particles. Okay, this is today's topic. And this is the comparison between chemical and mechanical polishing methods. In the mechanical polishing method, we use this kind of polisher or lap. This has the reference flat, and this reference flat could be copied onto the work surface from the topmost side. So by using this kind of configuration, and this one moves relatively. And this kind of configuration realize this kind of effective flattening. But flattened area has mechanical damage. So in contrast, in chemical etching, especially in the isotropic etching method, all the damaged layer could be removed. But there is no mechanism to remove to realize the flat surface or smooth surface. So this kind of method cannot be used generally as a flattening method. So this is our motivation. As you can see here, we like to use reference flat like this one, also in the chemical etching process. If this kind of reference flat is introduced into the chemical etching method, we can etch off the sample from the topmost side. So this means effective flattening from the topmost by purely chemically. Okay, so this is a really good process to realize the good performance of the substrate performance. Okay, to realize this kind of chemical etching method, following 3 points is very important. First one, relative species should be generated just on a reference flat. Okay, and the lifetime of the relative reactive species should be short. Then the reactive area is concentrated just on the surface of the reference flat. Then the topmost area of the sample could be etched off chemically, but this kind of bottom area cannot be etched off because the lifetime of the reactive species is too short. So this area is inreactive, non-reactive. So the from the topmost side could be etched off preferentially. This is very important to realize the flattening method. Okay, this kind of nature of the reference flat should not be changed during the process. So catalytic material that can generate reactive species is only the candidate of the reference flat. So the catalytic nature of the surface becomes very important in this case. So we called this process to be a catalyst deferred etching method, KEA method. Okay, and as a first trial of the KEA processing, we selected 4H silicon carbide, crystal silicon carbide as a material to be planarized, and we selected platinum as a catalyst, and it was selected as the etchant. Okay, why we use the platinum? The platinum reason is here. Platinum can dissociate many kinds of covalent bond molecules, and platinum has a moderate reactivity to the hydrogen, oxygen, and so on. This is a very important nature to be a good catalyst. And why we use the HF solution? HF is a very dangerous, looks very dangerous, but this molecule can be a source of very reactive elements, fluorine. And HF solution itself is quite inert, just against the silicon carbide. Silicon carbide is very inert material, so HF cannot cannot etch off without any catalyst. Okay, so we selected HF solution in this case. Okay, and this is the care apparatus. Maybe you can imagine this system. This is a care process system, and this system is nearly the same as that of the conventional polishing machine. This is a polishing part, and this is a sample, and the sample and the part moves relatively. So this is nearly the same configuration of the conventional polishing machine. But we use hydrogen fluoride solution, so polishing area is covered by plastic, and inside plastic, the anti-corrosive materials are used because we use the HF solution. And this is the details of the key apparatus. As you can see here, wafers here, and this is a catalytic plate. And this blue line is a catalyst. It's a thin film with the thickness less than 100 nanometer, very thin metal film. And in this case, we use a platinum thin film deposited on an elastic plate made of lava and so on. Okay, and the sample is pushed onto the catalyst surface softly by using a backside pressure, air pressure. Okay, and this is a typical status of the flattening. This is the SiC wafer, and just cut SiC wafer. And in this direction, there is some waviness. And during the care processing, from the topmost side, surface becomes flat, and flattened area is increasing, and finally all the area was flattened. This is the typical status of the flattening process using care method. And this is the macro and microscopic views of care processed surface. These are prepared by CMP method. In CMP-A, in macroscopic sense, the surface looks better, looks good. But in the microscopic sense, crystallographical property is not so good. In case of the chemical CMP process B, in the crystallographical property looks better than this one, but in macroscopic sense, surface is very wavy. But in case of the care process surface, in macroscopic sense, really flat, smooth surface is observed. And in the microscopic sense, the surface is perfect. As you can see, crystallographically perfect. This is the step and truss structure, and near the perfect surface. And you know, we found that the very interesting surface structure on the care process surface. As you can see here, the surface is consisting of regularly alternate wide and narrow terraces. It's a very strange structure. And as you can see, 4H silicon carbide has this kind of crystallographical structure. There are two kinds of layers, as you can see, HCP layer and FCC layer. And in case of the HCP layer, carbon is here just beneath the silicon. But in case of the FCC layer, there is no carbon just beneath the silicon. So 4H silicon carbide has this kind of two layers, and two layers are alternately stacked, as you can see here. And this is the line profile along this white line. As you can see, the step height is 2.5 angstrom, and this is relating to this height. So this is a one by layer step height. So this is a kind of a perfect structure. You know? And we checked the surface energy of this layer, and HCP layer and FCC layer. And we found that surface energy of FCC is a little smaller. And this kind of result was published from Physical Review B in 2008. And but I don't know, this surface is HCP or FCC. FCC has a lower surface energy, so this surface should be FCC, but we don't know FCC or HCP. So we tried to find this one by experimental method. We employed two kinds of silicon carbide. One is for its silicon carbide. In this case, HCP layer and FCC layer alternately stacked, as you can see here. But in case of the 6H silicon carbide, in this case, one HCP layer and two FCC layers, and one HCP layer and two FCC layers. So we employed these two. We found a care process surface. We checked the care process surface. So in case of the 6H SiC, you can see here the step and truss structure is like this. As you can see, narrow, wide, wide, narrow, wide, wide, narrow, wide, wide, narrow, wide, wide. As you can see here. So from this result, we can conclude wider truss is these two FCC layers. So by using this experimental method, we can conclude that wider truss is FCC, and this is good consistency to the this kind of surface energy analysis. Okay, this kind of analysis is not so important for the industrial application of the care process, but it was very interesting for me from the viewpoint of the surface science. And we concluded that this kind of strange step and truss structure is depending on difference between FCC layer and HCC layer. Okay, and we can realize this kind of surface in wafer scale. And this kind of wafer is very important, as I mentioned in the introduction. And this kind of good quality on the surface is very important for the R&D, research and development of the device fabrication. So we prepare this kind of substrate surface for the R&D people of the silicon carbide devices. And this is the result. This is the IV characteristics, one of the results. This is IV characteristics of Schottky barrier diodes prepared on silicon carbide surface, and we compared their property between the case with and without care processing. And we employed a reverse leak current result, and these results could be analyzed, and we can find very important parameters such as ideality factor and barrier height phi b. Okay, and these important parameters are plotted on this figure. And as you can see here, care process surface, these parameters are concentrated into this area. But in case of no care, the parameters are spread out, as you can see here. This kind of reproducibility is very, very important for the R&D of the fabrication of device fabrication development. So this care method highly contributed to the R&D of silicon carbide device fabrication in the initial stage of the device development. Okay, this is a very important role of us. We can prepare a very good surface, and this kind of surface is so important for the R&D of the device fabrication. Okay, and removal rate of this method is high enough, such as 400 nanometer power. This is nearly the same as that of the conventional CMP method. So this method works well from the viewpoint of the removal property, the removal rate property. Okay, but it looks very dangerous because we use the HF solution. So this method becomes more attractive one. But in this case, the care was applied to the gallium nitride wafer. Also, in this case, gallium nitride wafer becomes a step and truss structure. It looks a kind of perfect surface. And this is the CMP surface, and this surface becomes a step and truss structure within 5 minutes in the care process. So also in case of the gallium nitride device fabrication, this method works well to contribute to the R&D. Okay. And in case of the gallium nitride wafer, surface is so inhomogeneous. This is the surface morphology observed by selective etching method. As you can see here, there are many kinds of situations. And here is the low dislocation density area. And here, center of the island, this dislocation is concentrated into this area. And in this area, we found a very beautiful step and truss structure. And the intermediate area between two islands, the structure is so strained, as you can see here. The step line is curved like this, highly strained. And in this central area, we find many dislocations, as you can see here, here, and here. There are many dislocations, as we expected. Here, I like to say, in the chemical etching method, this kind of surface becomes very rough because this area or this kind of area could be etched off so fast. So the surface becomes very wavy and roughness becomes very large. But in case of the care process, the etching proceeds from the topmost side. So this kind of atomically flat surface can be obtained. Even in the case of this kind of a strained area and this kind of the defect area. In all the area, the surface becomes very flat within the 1 or 2 atomic layers. It's a very important nature of the care processing. Okay. So I'd like to talk about removal mechanism of this method. Our guess model is here. This is the platinum catalyst, and this is a silicon carbide. And as you can see, the care process surface has step and truss structure. So removal mechanism is step flow. So the silicon removal at the step edge is more essential in this case. So we checked the etching process at the step edge. And in this case, this is the initial state. We put the HF solution, HF molecule here, and HF molecule could be dissociated due to the platinum, and F minus can adsorb here the step edge silicon, and because of this kind of strong risk-based nature and the strong nucleophilicity. So this kind of element can adsorb here to make a hypervalent situation. In this case, 5-fold coordination is appearing. And but in this case, this kind of triangle is constructed by sp2 hybridized orbitals. And in this line, bonding is prepared by p orbitals. So this strength of the back bond could be weakened from the compared with this kind of a 4-fold coordination situation. So back bond could be broken by proton transfer from here to here. This is our guess model, and I try to simulate this kind of reaction by using a first principles analysis. And in this case, we use simulation tools for atomic technology state program package. This is developed by Morikawa Sensei of Osaka University, and we use this one. And we use these kind of pseudo potentials for silicon and CHOF platinum and so on. And cutoff energy here was like this. And to understand the barrier height of this reaction, we use CINED method. And calculations are performed at 0 Kelvin, and any influence of water molecule as solvent is neglected in this calculation. Okay, this is the calculation methods, summary of the calculation methods. And these are snapshots during the actual simulation. As you can see here, this is the initial state. We put the HF molecule here, and as you can see here, step edge, this is a step edge silicon, and this area is a wide space. This area has wide space, so we can put HF molecule here. And in this simulation, we found a metastable state here, and in this case, F minus adsorbed at the silicon, step edge silicon, and five-fold coordination situation was observed as expected. And after that, as a final state, the back bond was broken, as you can see here, and proton by a proton transfer from here to here. And this carbon was dominated by hydrogen, and silicon becomes four-fold coordination. Four-fold coordination is the best coordination for silicon. And back bond was broken, and this is the simulated result of the K etching mechanism. Okay, and this is a reaction pathway and energy diagram of this HF-K process for the silicon carbide. In the case of the initial state, HF molecules here, and then at the metastable state, intermediate state, the step edge silicon is terminated by additional F element, and situation is hypervalent situation. And back bond was broken at the final state. And these red dots means the energy diagram of this reaction. As you can see here, the barrier height of this reaction was calculated to be 0.8 eV. This is low enough to proceed under room temperature. But in case of the no platinum case, as you can see here, this kind of five-fold coordination situation is very, very unstable, as you can see, compared with the platinum case. So due to this kind of instability, the barrier height in this case is 2.1 eV. This is high enough, too high to proceed under room temperature. So the most important role of the catalyst is as follows. First one, it could dissociate HF molecule, assist to dissociate HF molecule due to the this kind of H platinum interaction and F silicon interaction. And second one is the stabilization. This one is the most important, stabilization of the metastable states from here to here. You can see this is the important stabilization. And due to this kind of stabilization, reaction activation energy goes down from here to here. So this is the most important role of the catalyst. Okay, we found this kind of situation. And this is the another viewpoint. This is the energy dependence on PT position. As you can see, the horizontal axis means in this direction, the distance between the PT, platinum, and the silicon carbide is closer. And in this direction, platinum and distance between platinum and the silicon carbide becomes more wider. And this white circles means initial state energy. And initial state energy goes up continuously with the decrease of the distance between platinum and the silicon carbide. just repulsive. But in case of the metastable and final states, as you can see here, the energy is stabilized, and going up. So this kind of stabilization is coming from this kind of interaction, this interaction between platinum and the silicon, platinum and the oxygen. If the distance between the platinum and the silicon is larger, then this kind of interaction becomes weak and the relative energy becomes high. But at the appropriate distance near here, this kind of interaction is the most appropriate situation, as you can see here. And more smaller distance, it becomes repulsive. In this area is very important. And in this area, the energy difference between this one becomes very small. So it becomes easy to jump from the initial state to the metastable states and metastable states to the final states. So this kind of uh, situation of the energy situation is very important. And this area, etching process never proceed. But in this area, etching process becomes easy to proceed. Okay, so this interaction is very important. So this is the most important role of the catalyst. And this is another evidence of the interaction between the oxygen and the platinum. This is the local density of state analysis of the PTO bond. In this case, we selected PZZ bond atomic orbital for this platinum, and PZ atomic orbital was selected for this oxygen. And these are calculated density of states at this area. And we found a bonding situation here. The both dose becomes larger in this case, in this area. And if the distance between platinum and silicon carbide becomes longer, distance becomes larger, then the bonding situation shifted from this area to this area, to the unstable situation. So this kind of stabilization from this to this is the most important phenomenon to reduce the activation energy in this care processing. Okay, this is a very important analysis to understand the real nature of this kind of situation. Okay. Okay. So far in care process, we found key phenomena is the hypervalent silicate at the step silicon. And due to this hypervalent silicate, the backbone becomes longer and weakened. This is a very important phenomenon. We found that. But so in the HF care process, F minus works as a strong rich base with high nucleophilicity. So this kind of strength of the as the rich base is the most important nature of this F minus to realize hypervalent silicate. But you know, OH minus has also strong rich base with high nucleophilicity. So a water molecule becomes possible to be another candidate for HF to realize hypervalent situation. So if this is possible, water care becomes possible. It looks very good for us from the viewpoint of eco-friendly, environmentally friendly process. So in this case, the etching mechanism was indirect dissociative absorption of HF molecule, but in this case, mechanism becomes indirect dissociative absorption of a water molecule, and this has a name, hydrolysis reaction. Okay, so if this is possible, this becomes possible, care process becomes more environmentally friendly. Okay, so first of all, we checked by using an experimental method. This is a water care for the silicon carbide. As you can see here, this is a pre-machined surface, and this is a post-process surface. As you can see, this distorted surface becomes very beautiful. And along this AA line, you can see here, the very beautiful step and structure was observed. And the step height in this case was also 2.5 angstrom. It's a 1 by layer distance between the silicon carbide structure. And this is a kind of perfect surface. So water care looks good. Water care works well. And then this method is utilized for the planarization of the epitaxially grown silicon carbide. After epitaxial growth, surface become like this. This is due to the step bunching during the epitaxial growth. So this rough surface is not so good for the following device processing. So this kind of roughness should be removed just after epitaxial growth. Okay, and to remove this one, water care is used. And as you can see here, by applying this water care process, within 3 minutes, so this kind of rough surface becomes atomically flat, as you can see here. And this is very important. And as you can imagine, this kind of method is very friendly to the clean room usage. Fabrication of the device was done inside the clean room, and all the process should be attractive to the clean room usage. And this water care is very attractive to the clean room usage. So this kind of method is used for the roughness removal after epitaxially grown silicon carbide surface. Okay. Okay. So this is a guess model of the water care. You know, this is a water care. So this is very, very friendly to the usage inside the clean room. And this is a guess model of the water care. And our guess model is based on indirect hydrolysis reaction, nearly the same as that of the HFK method, HFK process. As an initial state, water molecule here, and due to the platinum nature as a catalyst, it could be dissociated, and OH minus could adsorb the silicon, step-edge silicon, due to this strong Lewis-based nature with the high nuclear ferocity. And this kind of hypervalent situation was expected. And in this case, back bond becomes weakened, and back bond could be broken by proton transfer from anywhere to here. This is our guess model for the water care. And actually, we simulated this kind of situation. These are snapshots. As you can see here, water molecule is put here as an initial state. And we found at the metastable states, we observe the hypervalent situation here as expected. And then the back bond was broken, as you can imagine, as our expectation. And energy diagram is here. As you can see, the reaction barrier is reduced to 0.7. It's low enough to proceed under room temperature. And in case of no platinum, the barrier height was 2 eV in this case. So also in this case, the five-fold coordination situation was metastable state. It stabilized from higher state to very low state. This is very important. This kind of stabilization is also important, also in this case. Okay, and yeah, and this kind of very high activation energy is the kind of evidence that silicon carbide cannot be dissolved into the water without any catalyst. Okay. So the HF could be used to planarise the silicon carbide surface. But I already mentioned this method cannot be used widely because HF is very corrosive, and so corrosive to be used, oxide materials and so on, even in the case of no PT. Okay, so these kind of material automatically dissolved into the HF solution, so we cannot realize K configuration. So, but in case of the water care, we can apply this method for many kinds of application. Okay. So this is the hydrolysis reaction, and actually simulated by using a state program, and also in this case, and as you can see, oxide material hydrolysis reaction proceed more easily when the bonding ionicity becomes higher. And in case of the oxide materials, the bonding ionicity becomes higher than that of the SiC or gallium nitride. So this kind of material is more appropriate for the water care. And the water care can accept these kind of materials because we don't use HF solution in the water care. And this is a reaction pathway and energy diagram, as you can see here. In this case, the red line is energy diagram from the initial state to the final state. The activation energy is low enough to proceed under room temperature. But in case of no platinum, even in the case of the silicon dioxide, the activation energy was very high. So it is a kind of evidence. Glass material cannot be dissolved into the water automatically without if there is no catalyst. Okay, and so these are actual application to many kinds of materials. The sapphire, zinc oxide, and silicon dioxide was planarized, as you can see here. And this is not oxide, but aluminum gallium nitride is a very important material for the next generation semiconductor fabrication, semiconductor industry. And this kind of surface could be planarized, as you can see here, to be a very beautiful surface. And I'd like to introduce something optical surface application. This is the planarized surface of the quartz glass. As you can see here, roughness is really small. That's 0.5 angstrom, lower than 0.5 angstrom. And this is a world's smoothest surface. And this surface is intentionally used for the EUV and X-ray optical components. Okay, this kind of surface is actually utilized in this kind of optical components. And this is another application. This is atomic smoothing of the YAG ceramics. YAG means yttrium aluminum garnet. This is a very important laser medium, you know. So for the laser medium, surface should be flat to reduce the surface scattering of the light. So this kind of atomical smoothness is very important to reduce the surface scattering, and for the as the laser medium. And in this case, this is a pre-machined surface, currently best surface, and this is a care process surface, and this is a height histogram of these surfaces. In case of the as received surface, the height histogram is distributed like this. But in case of this care process surface, the histogram is concentrated into the zero area. The width of the distribution is like lower than 0.5 nanometer. So atomically flat surface was realized even in the case of this kind of a polycrystalline structure. In some cases, if the surface is just perpendicular to the lower order surface. Then in this case, in some cases, this kind of step and truss structure was observed. This is evidence that evidence of the removal mechanism of this one is based on a chemical, not mechanical. Okay, and this is the final application to the optical elements. And this is the SOB, strontium boron oxide. This is the most cheap material for the window on the shutter wavelength interface. And by using this kind of a material, the damage threshold against DUV laser radiation becomes higher and higher. This is, so far we use this kind of calcium chloride, but the SOB becomes higher performance. And surface is planarized by using a care, the performance becomes included from here to here, increased from here to here. So the surface quality of this one, of the window, is very important to heighten the damage threshold. Okay, and this is the final application. You can see here, this is a wettability controller in nanostructure. We like to realize this kind of surface. In the hole, they should be coated by a silicon dioxide, and this area to be hydrophobic, it should be coated by carbon. And to realize this kind of structure, we prepare the layer, carbon layer, and then we prepare the silicon dioxide layer. And in topmost area, silicon dioxide layer should be removed. Then we can realize this kind of surface. To realize this kind of things, photo lithography is one of the candidates, but a very high cost process. So this should be, only this area should be removed. So we applied care process. In the care process, silicon dioxide is easy to be removed, but carbon layer is not so easy to be removed because hydrolysis reaction doesn't occur on the carbon layer. So carbon layer works as a stopping layer of the water care. And after that, we realize this one. As you can see, before the development of water care, this kind of method was considered to proceed by using a conventional polishing method, using a powder particles. But in case of the, if we use a polishing method, if the powder particle goes inside the hole, we can never remove the powder particles. As you can see here, the diameter of the hole was about 200 nanometer. So if the particles go inside, then we cannot remove this one by using any kind of cleaning method. So the powder particle in care process not use powder particle. So care process looks very appropriate to be applied to this kind of surface preparation. Okay. Okay. So the in care process, the catalyst is very important. In the HF care process, the platinum was only the catalyst to be used inside a very corrosive HF solution. But now we are in the water care situation, so we can use many kinds of metals as a catalyst. So the removal rate is strongly depending on metal element. So now we are trying to realize and try to find a more effective catalyst by using alloy technique and by using first principles calculation, also by using our experimental method. In the near future, this kind of water care method becomes more effective by finding a new appropriate catalyst. Okay, this is our future research plan for the improvements of care process. Okay, this is the summary. We developed the care process as a chemical planarization process, and silicon carbide was planarized and water care becomes possible. And this is most important. Conventional polishing machine becomes water care machine by just changing the path from non-catalytic to catalytic. Just by changing the paths, all the machine becomes water care. So I hope this method contribute for many kinds of industrial field. Thank you very much for your kind attention. This is a collaborative work between many kinds of people, and we got funding from governments and company. Thank you very much for your kind attention.
Thank you, Yamauchi Sensei, for your nice talk. Actually, we have very short time for question session. We have one question here, Sensei, in the Zoom chat box.
Oh, really?
Yes, this is from one of our participant.
Okay.
He asks, using a D-band center model, could you show us how the mechanism of bonding silicon HF platinum, how could be possible?
Just a moment. I cannot reach the chat box. Just a moment.
Yes.
I'm so familiar to use Zoom system, so now. Okay, chat.
Chat. Yes. How could be possible a bonding mechanism between silicon, HF, and platinum happens during the process?
Yeah. So so maybe we can use this one.
Mm.
Yeah, eight. So the reaction from here to here. Okay. So the question
Yes.
is on the reaction from here to here.
Yes.
The HF molecule has the highest strong binding energy. So the association is very difficult, as you can imagine. But in case of with a kind of a catalyst, the H and platinum interaction can gain the and interaction in fluorine silicon gain the energy. So the gain energy and is so large in this case. So this HF could be dissociated by the assistance of the interaction between these atoms and these atoms. So then the dissociation energy is reduced from so large energy to just 4.7. So from here to this is the barrier height to dissociate HF molecule.
Okay.
And after that, F can easily adsorb here because of the strong weakness. Okay. Okay.
Okay.
Is it-
Okay. Thank you.
okay. And if you have any questions, please send me by using an email and so on, so I can answer them. I'm sorry, I used so long time for this presentation.
Actually, there is one more question, Sensei.
Yeah.
This is from Ian Mitran.
Yeah.
Asking, wondering what is the contribution of charge in the polished surface?
Charge of
The contribution of charge in the polished surface.
charge in the polished surface.
Yes.
What mean? Charge?
Yes.
Charge is electric charge
Yes, electronic charge in the Polish surface.
and for surface.
Yes.
So
You
I
have
never think about the
HF.
HF.
Yes.
Yeah. So the charge. Okay. So the maybe I don't know the so in this case one electron is come inside in this but in this calculation we never remove the charge from this graph. So
Mhm.
I don't know the details, but the maybe this area could be negative charged up, and some electrons uh, diffuse inside. But I don't know. Finally, the charge here, atomic charge of the ion is not calculated.
Okay.
Okay.
Okay. Thank you for your lecture and explanation,
Mhm.
Yamauchi Sensei.
Yeah.